Hi everybody, this is Dr. G. Amarendra Rao, Department of Mechanical Engineering, Vijnana Bharati Institute of Technology, Hyderabad. Today we'll be discussing about analysis of extended surfaces. Extended surfaces are also known as fins. Basically, fins are used to enhance the heat transfer rate from the given surface. And this happens due to the increase in area available for heat transfer. And as you are aware, in any mode of heat transfer, maybe conduction, convection or radiation, heat transfer rate is directly proportional to the area available. So any attempt to increase the area will definitely increase the heat transfer rate. Therefore, the underlying principle of extended surfaces or fins is to provide an extra area for the heat transfer to take place. And fins are used in many mechanical and electronic and electrical systems like air-cooled IC engines, air-cooled compressors, on the surface of electronic instruments, electrical transformers, motors and generators. And here I would like to emphasize the word air-cooled. It is due to the fact that fins are found to be more effective in media with low values of convective heat transfer coefficient, like when the medium is air, gas, etc. We never ever use fins on water cooled systems or oil cooled systems. We never, because of tremendous value of H. And fins attached to an air cooled system would be more effective than water cooled or oil cooled systems. Continuation of what I am talking about. And depending upon the application, one can have variety of fins. Typically integral fins and independent fins. When I say integral fins, they are a part of the total system. Or integral fins are provided onto the system at the time of basic manufacturing process, like casting. We are going to have a provision for extended surfaces. Independent fins, when I say, they are attached to the system later on by some joining process, maybe welding, brazing or soldering, depending upon the dimension of the fins. Again, integral fins or independent fins could be of two categories. Fins of variable cross section. So the area of cross section may diminish as you go away from surface, or the area of cross section may increase as we go away from the surface. And in practice, fins with a variable cross section are preferred due to less space required to accommodate them. And space becomes an important criteria in automobiles, in aircrafts and other applications. And on the other side, one can have fins having uniform cross section. Doesn't matter where you are located, you are going to have same area. Fins of uniform or variable cross section could have different cross sections, maybe circular fins having circular cross section, triangular fins, equilateral triangular cross section, square fins, rectangular fins. They are mathematically defined fins. Sometimes fins may have elliptical cross section, fins may have aerofoil cross section, trapezoidal cross section. So depending upon the cross section, one can have so many varieties of fins. Then fins of any cross section could be further classified into three types. Very long fins, length is going to be too much. Length is going to be too much compared to the diameter, if at all it's a circular fin, like a long wire, long rod. Then short fins with end insulation. L is almost equal to D, but we ignore the end contribution. end losses will be insignificant. Then short fins with free end. L is very close to D, but we consider the end losses. And we realize that a fin can lose the heat from its lateral surface. When it's a lateral surface, I mean P into L, it may lose it from the end. And it may be noted that P represents perimeter of the fin, circumference of the fin. Later on, we will have a mention about P. And to simplify the mathematical process, the analysis would be carried out under certain hypothetical assumptions. I am using the word hypothetical because in practice it's not going to happen. First and foremost is heat transfer is one-dimensional and steady. That is, temperature is a function of X alone, nothing more than that. Then fins would have uniform cross section, that is, area doesn't vary with location. And fin material is homogeneous and isotropic. When I say homogeneous and isotropic, it's going to have uniform properties all along. Among all the properties, thermal conductivity becomes very important, and thermal conductivity does not vary with location. Then thermal conductivity, the one which we are talking about, is a function of temperature, but here to simplify the life, thermal conductivity is same irrespective of the temperature we talk about. Then fin is exposed to a medium of uniform heat transfer coefficient. Which means that H is independent of location. All along you got same medium. Then absolutely no concern about the radiation. We ignore the radiation effects. And we realize that in fins we are going to have heat transfer by combined modes. Conduction along the length and convection over the surface. So if we pick up this as a surface and we attach a fin, then we are going to have conduction along the length inside and convection over the surface. Conduction is taking place across the area A, and convection is taking place across the perimeter PL. Therefore, we don't have any ready-made solution for this type of problems. We cannot even use electrical analogy because of these peculiarities. Therefore, we need to go down to the scratch. When I say scratch, we need to somehow obtain the GD, governing differential equation, for the temperature distribution. That can be obtained by using the first law of thermodynamics, Fourier law of heat conduction, Newton's law of cooling, of course, Taylor series. And for this purpose, we propose a problem like we have a hot surface at Ts, to which we attach a fin made up of some material K having some cross section of perimeter P and area A. Then we pick up an elemental strip anywhere at any x from the surface, some thickness dx. Then we assume that del Qx is the energy coming into the element by conduction. Del Qx plus dx is the energy going out of the element by conduction. And del Qc is the rate of energy going out by convection on the perimeter. And for this elemental strip to be in equilibrium, energy coming in by conduction should be equal to energy going out partly by conduction and partly by convection. This is the first law of thermodynamics, the so-called energy balance equation. Then we invoke the basic principles of Fourier law. Del Qx is equal to minus Ka dt by dx. Then del Qx plus dx we expand into Taylor series. Del Qx plus d by dx, del Qx dx. Then del Qc is calculated using Newton's law of cooling, that is H into A, that area available is P into dx into T minus T infinity E, where P is the perimeter, T is the temperature of the element. Then Pdx, as I was talking, is the peripheral area of the element. P is the perimeter. Then we substitute for del qx plus dx and del qc in the energy balance equation. Then we do routine mathematical processing to arrive at the energy balance equation in this format. D square t by dx square minus hp by ka times t minus t infinity is equal to 0. To make this equation mathematically compatible, we introduce two parameters like theta is the temperature difference at any location and m square hp by ka per meter square. And once we implement these definitions here, we are going to have this equation reduced to d square theta by dx square minus m square theta is equal to 0. And this is the governing differential equation for the temperature distribution in a fin of uniform cross section subjected to one-dimensional steady state conditions. And one can observe that it is an ordinary differential equation of second order. And from standard mathematics, it will have a solution in the form of equation 3, theta is equal to t minus t infinity is equal to c1 e power mx plus c2 e power minus mx, where c1 and c2 are the unknown constants to be evaluated using appropriate boundary conditions. And depending upon the sort of boundary conditions, we are going to get c1 and c2 and accordingly the temperature distribution. We begin with one of the simplest cases of a very long fin. That is, theoretically, length of the fin stretches up to infinity. Then this long fin is made up of material K, cross section P and A is attached to a surface at TS. Then we try to create a coordinate system just below this. Along x-axis, distance from the surface, along y-axis we have the temperature, and we know that at x is equal to 0, t is equal to ts all along. The fluid temperature is T infinity. And this temperature difference theta s we call it as surface temperature difference Ts minus T infinity. And we are interested in calculating temperature at any x position. And before we ponder over that, we will try to have a look at details of area of cross section, perimeter and m for different cross sections. Circular cross section perimeter is pi d, area of cross section pi by 4 d square, and if you substitute in the general equation hp by k, it's going to be 4h by kd. And if you go for square cross section, perimeter is 4 times the side, area is a square 4h by ka. And if you pick up a rectangular cross section of height a and width b, then the perimeter is 2a plus 2b, that is 2 times a plus b, area is ab. Then if you implement it, your m square is going to be 2h a plus b by cab k into ab. These are all the theoretical cross sections. And if you take any complex cross section like aerofoil, elliptical, trapezoidal, the values of p and a will be measured and they will be available to us directly. Like I may say p is equal to 110 centimeters, a is equal to 88 centimeters square, something like that. They will be available. So by some experimental methods will be used for the purpose of this perimeter and area, and we have to use them and get the values of C1 and C2. Here boundary conditions will be at x is equal to 0, theta is theta s. It is a universal boundary condition for all the cases. And at x is equal to infinity, theta is equal to 0. Because there is nothing to separate between the surface and the fluid when you are far away from the surface. And we realize that some standard values of exponential and hyperbolic functions with which we will be concerned in this topic. E power 0 is 1, e power infinity is infinity, e power minus infinity is equal to 0, e power 1 is 2.718, e power minus 1 upon this 0.3678. Sin hyperbolic x e power x minus e power minus x by 2. As a result, sin hyperbolic 0 will be 0. Cos hyperbolic x is e power x plus e power minus x by 2, and cos hyperbolic 0 is equal to 1. Obviously tan hyperbolic x will be sin by cos, so you can always go for that. And when you implement these two boundary conditions and use the standard values, we realize that C1 will vanish, C2 will be theta s, and when you substitute back for this in the general equation, we get theta by theta s as t minus t infinity, but Ts minus T infinity is equal to e power minus mx. This is the temperature distribution in a long fin subjected to the standard assumptions, and we can notice that this is going to be an exponential function. And we will be dealing with two types of problems. Some location is given, calculate the temperature. Good, we can calculate it. Some temperature we want to reach, how long we have to go away, right? Calculate the location. This we call it as a forward problem, this we call it as a backward problem. If both of them are furnished, we'll be missing some other data. Definitely one equation, one unknown. And we realize that the nature of this temperature profile depends upon number of parameters, particularly fin material, the medium, and the fin size. If it is circular, the diameter. And it can be shown that the profile is going to be flat, horizontal, when k is infinity, perfect conductor. When h is 0, the fin is placed in outside space, perfect medium. And when d is infinity, fin diameter is very big. And the profile will coincide with the ordinate y-axis when k is nothing, perfect insulator. When h is infinity, very big, like a condensing gas, condensing vapors, or when d is nothing. These are all the two hypothetical cases, and for all the practical cases you are going to have temperature profiles like this, and the profile will become flatter and flatter. That is desirable as we increase k when we go for a better material. Definitely copper fins are superior to aluminum fins, or when we place it in a poor medium. So air-cooled fins are better than water-cooled fins. Fins placed in 15th floor are better than fins placed in ground floor. Fins used in aircrafts are better than fins used in trucks or buses. That is the meaning of it. Or when you increase the diameter, 30 mm is better than 20 mm, something like that. So in order to improve the overall performance of the fins, the curve must be as flat as possible. And curve can be made flatter by these three methods. Go for a better material, use it in a poor medium, go for the maximum possible diameter, satisfying other conflicting requirements. Then one can calculate the heat transfer rate from the fin. This can be done by using either Fourier law, that is heat transfer rate is pure conduction at the surface, or Newton's law is going to be 100% convection over the surface. And by both these methods, one can realize that the heat transfer rate from the fin will be cam theta s. If you are using number of similar fins, then the total heat transfer rate would be n times cam theta s, where n is an integer. You may use 10 fins or 100 fins, 150 fins, having identical characteristics. Then we will be always interested in the performance of the fins. The first performance parameter would be fin efficiency. It's a measure of thermal performance of a fin. And obviously it must be as much as possible for a better performance. Then basically efficiency represents the ratio of actual heat transfer rate to the maximum possible heat transfer rate. Mathematically we can say that efficiency is Q by Qmax, where Q is the actual heat transfer rate and Qmax is the maximum possible heat transfer rate. And Qmax can be obtained by the equation HPL theta s, where PL is peripheral area of the fin. And you can always show that for long fins, efficiency is given by 1 upon ml into 100. And you can see that under actual conditions, the temperature profile is something like this for the given material, given cross section, given area, and given medium. And if you assume that the fin is attached to a surface at 200, outside temperature is 20. As we go away from the surface, temperature is diminishing, you can see. As a result, the temperature difference available between the fin and the fluid is continuously decreasing. Therefore, different parts of the fin, different segments of the fin will contribute differently for the given heat transfer rate. The segments which are nearer to the surface will have more contribution. The segments far away from the surface will have meager contribution. This is reality. Under these conditions, heat transfer rate is given by cam theta s. Okay. And in order to have maximum heat transfer rate, each and every segment should contribute to the maximum possible extent. That can happen only when the fin is maintained at the surface temperature all along its length, so that everywhere the temperature difference is same. This will happen only when K is infinity. When I say K is infinity, absolutely no conduction, because temperature is same everywhere. Therefore, your maximum heat transfer rate has to happen only by convection. H into area available, PL into theta s. Here we introduce the term L. Although we are talking about very long fins, L becomes important, and we realize that L is going to be too much compared to the size of the fin or diameter of the fin if it is circular. So that way you can always calculate the fin efficiency. And remember, actual heat transfer rate is by combined modes, conduction as well as convection. But maximum heat transfer rate is only by convection, because conduction is prohibited due to same temperature all along. Then we talk about another parameter called as fin effectiveness. And fin effectiveness is a measure of the cost aspects of the fins. Whenever you are going for fins, it involves so much of cost. You have to purchase the material, maybe copper, maybe aluminum, it involves some cost. And you have to manufacture it, you have to go for various mechanical processes, it involves some cost. And you have to maintain the fins, again there is cost. And you have to provide some space for the fins, that becomes very crucial in automobile applications. Again that involves some cost. At the end of the day, we must make sure that whatever cost we are bearing is very much overshadowed by the benefits we get. And that can happen only when we go for the effectiveness calculations. And the effectiveness has to be as much as possible for the fins to be cost effective and economical. Then it represents the ratio of heat transfer rate with fins to the heat transfer rate without fins. What is that you are getting without fins, and what is that is your ambition? And it should be at least 2.5 for the fins to be economically viable, which means that heat transfer rate with fins should be at least 2.5 times heat transfer rate without fins or bare surface. Mathematically, effectiveness is Q by Q bare. Q is heat transfer rate with fins, Q bare is heat transfer rate without fins. And remember, Q is cam theta s, it is combined modes, and Q bare is HA theta s, it is pure convection, which means that whatever surface you have is losing heat on its own. There is nothing that you are separating. Some area is there, medium is there, surface at Ts, medium at T infinity. It is as simple as that. So it is losing on its heat on its own by pure convection. Then if you implement both these equations here, your effectiveness is going to be Km by H. So you can calculate effectiveness, and if you realize that it is more than the threshold value of 2.5, you can say fins are S, you can recommend. Otherwise, you can discard the idea of fins. Similar way, one can go for case B, short fin with end insulation, and you can do same sort of analysis, and you can get temperature distribution as cos h ml minus x by cos h ml, Q cam theta as tan h ml, efficiency tan h ml by ml, effectiveness is going to be Km by H tan HML. And you can see if L is too much, tan HML will be equal to 1. So for very long fins, all these equations will go back to the earlier case. Right. Now this mathematical part one can do by using same standard procedure. Then one can go for slightly intricate case, short fin with free end. So end is allowed to lose the heat. Again one can apply appropriate boundary conditions and you can get slightly lengthier equations for temperature distribution, heat transfer rate, efficiency and effectiveness. Right. And one can have so many other cases and appropriate boundary conditions can be applied and C1 and C2 can be evaluated. And we realize that for all these cases, Qmax is HPL theta S and your Q bare is HA theta S. Both of them are happening only by convection, pure convection. Okay. And these equations can be used in order to solve quite a number of problems. Now let us pick up some numericals of previous engineering services. First problem is two long rods of same diameter, one made of brass case 85 and the other made up of copper case 375, have one of their ends inserted into a furnace and both are exposed to same environment. At a section 10.5 centimeters away from the furnace end, the temperature in the brass is 120 degrees centigrade. At what distance from the furnace end, same temperature would be recorded in the copper rod? This problem has been given for full 20 marks way back in 1993. Of course, derive the equation used that may carry 10 marks. Solution may carry 10 more marks. And if you jot down the data, rod 1 brass K1 85, rod 2 copper K2 375, and furnace is same at temperature Ts, same medium H comma T infinity, and physical arrangement is shown over here, and both the ends are into the furnace, other end is exposed to the medium, very long rods, same geometry, areas are same, perimeter is same, materials are different. This is brass, this is copper. And if you see the temperature profiles, definitely copper will be flatter because K is very big and brass is going to be steeper. And for copper we have seen that K is as much as 375, for brass it is only 75, right? Then you want to record a temperature of 110 degrees centigrade, that is given 110. Then you are traveling by x1, that is brass, and how long you have to travel in copper, x2 you want to calculate, x1 is available. Then you have to use the equation for long fins, theta by theta s is e power minus mx, and theta t minus t infinity is constant, this temperature is fixed. Same perimeter, same area, same medium, they are all fixed. Then you can take logarithm on both the sides. You are going to get mx is equal to constant. M is square root of hp by ka into x is constant. Then perimeter is same, h is same, area is same. Therefore, you are going to get x1 by root k1 is equal to x2 by root k2, or x2 is equal to x1 root of k2 by k1. x1 is 10.5, k2 is 375, k1 is 85. And if you calculate, you are going to get x2 is equal to 22.05 centimeters. So same temperature in copper rod will be obtained at shade over 22 centimeters from the furnace end. This is the problem. Then another problem given in 2004 for just 7 marks, simple problem. An electronic semiconductor device generates heat at a rate of 0.48 watts. In order to keep the surface temperature at the upper limit of 70 degrees centigrade, the generated heat is to be dissipated to the surroundings at 30 degrees centigrade. To accomplish this task, aluminum pins of 0.7 mm square cross section and 12 mm long are attached to the surface. The thermal conductivity of aluminum is 170. If the convective heat transfer coefficient of air is 12 watts per meter square Kelvin, calculate the number of fins required. Assume end insulation. If you jot down the data, total heat generated is 0.48 watts. Surface temperature 70, fluid temperature 30. Size of the square is 0.7 mm, 0.7 10 power minus 3 meters. Then L is 12 mm, 0.012 meters, K 170, H is 12 in respective units. This is the physics of the problem. This surface is a TS, right? Medium is H comma T infinity, length is L, cap and all those things. First we calculate area of cross section of square A square, 4.9 10 power minus 7 meter square. Remember, you have to have data consistency or dimensional consistency. Linear dimensions have to be in meters. Areas must be in meter square, volumes must be in meter cube. Here you can see the side of the square and length are given in mm. Immediately have it in meters so that you will not be having any inconvenience. Then area is 4.9 10 power minus 7. Then perimeter is 4 times A. Then if you calculate it, you are going to have your M as 20.08 per meter. Because for square cross section, M is root of 4H by Ka. This area we require at the time of heat transfer calculations. Then calculate ML. It's going to be 0.24096. Tan HML 0.2364. Then Q is going to be cam theta s tan HML. Cam theta s tan HML. And if you implement all this, heat transfer rate from each fin would be 0.0158 watts. Then Q total should be equal to N times Q. N times Q. So 0.48 is the total heat generated is equal to N into 0.0158. And if you calculate N, it is going to be 30.34. Number has to be integer. So we require 31 fins in order to take care of the heat generated in the fin. The next problem given in recent 2012 for 10 marks. A rectangular fin of length 30 centimeters, width 30 centimeters and thickness 2 mm is attached to a surface at 300 degrees centigrade. The fin is made up of aluminum K204 and is exposed to air at 30 degrees centigrade with H is equal to 15. The end of the fin is uninsulated. You can see here it says uninsulated and is free to lose heat. Determine the temperature of the fin at 30 centimeters from the base, that is at the end. The rate of heat transfer from the fin efficiency. And if you look at the data, length is 30 centimeters, 0.3 meters. Width is 30 centimeters, means all along it is there, 0.3 meters. Thickness delta is 2 mm by 1000, 0.02 meters. And if you look at the physics of the problem, this is the hot surface, this is the fin of length L, width W, thickness delta. Right, and you can always find Ts 300, T infinity 30, theta S 270, K 204, H 15. And from this you can always calculate the perimeter, which is going to be 2 times W plus delta, 0.604. Area W into delta is going to be 6 into 10 power minus 4. Then first thing calculate M, root of HP by Ka, 8.603. Then find ML, 2.581. Then calculate sin HML, 6.567, cos HML, 6.643, tan HML, 0.988. Then H by Mk, that's also required in uninsulated fins, 8.546, 10 power minus 3. They are all dimensionless. Then temperature distribution in a short fin with free end is given by theta by theta s is equal to T minus T infinity by Ts minus T infinity is equal to cos h m L minus x plus h by mk sin h m L minus x by cos h m L plus h by mk sin h m L. Please note that the first term in the numerator and denominator account for the lateral contribution and second terms take care of the end contribution. And we realize that end contribution is going to be very small compared to the lateral contribution. That we are going to realize a little later. Then at x is equal to L, temperature at the end, at the free end. So theta by theta L, TL minus T infinity by TS minus T infinity is equal to 1 by cos HML plus H by MK sin HML. Because sin H0 is 0, this is gone. Cos H0 is 1. And if you make the calculations, you are going to realize that temperature at the free end is 70.299 degrees centigrade. Then heat transfer rate is given by cam theta s tan HML plus H by MK by 1 plus H by MK tan HML. Again, first terms account for lateral contribution, second terms account for end contribution. See, lateral contribution 0.988, end contribution 8.546 10 power minus 3, absolutely small. Right, then you can substitute for K 204, then A and M theta S, and you realize that heat transfer rate will be 280.94 watts. The efficiency is given by 1 by ml times tan HML plus H by MK by 1 plus H by MK tan HML into 100. And if you work out, it's going to be 38.285 percentage. This is a problem given in 2002. Finally, we'll take up a practical problem given in 2018 for 20 marks. A very long cylindrical rod of 30 mm diameter has one of its ends attached to a surface at 500. Entire length of the rod is exposed to a medium at 25 degrees centigrade with H is equal to 25. Temperature along the length of the rod at x1 is equal to 400 degrees centigrade. At x1 plus 10 mm is 390 degrees centigrade. Then determine thermal conductivity of the rod material and the value of x1 where temperature is 400 degrees centigrade. Right. First, let us jot down the data. Diameter is 30 mm by 1000 0.03. TS is 500. T infinity 25. Theta is 475. H is 25. Then at x is equal to x1 meters, T is 400. At x is equal to x1 plus 10 mm by 1000 0.01 meters, T is 390. And we are interested in K and x1. So the data is something like this. We have the long fin attached to a surface at TS. And fin has a circular cross section exposed to a medium of H comma T infinity. At x is equal to x1, temperature is 390. At x is equal to x1 plus 0.01, temperature is 390. At x is equal to x1, temperature is 400 in fact. x1 plus 0.01, it is 390. Then find the value of K. So you need to calculate the slope. That is the meaning of it. At what rate the temperature is dropping, that has to be estimated. Then for long fins, we have the temperature distribution given by this. Then at x is equal to x1, if you substitute 400 minus 25 by theta is 475 is equal to e power minus mx1. Therefore, we get mx1 is equal to 0.236. Then at x is equal to x1 plus 0.01, we have 390 minus 25 by 475 is equal to e power minus m x1 plus 0.01. From this we get m into x1 plus 0.01 is equal to 0.2634. Then we take the ratio of B to A, equation B by equation A. To get m x1 plus 0.01 by m x1 is equal to 0.2634 by 0.236. And we can always cancel out m, right? When we cancel out m, we are going to get x1 plus 0.01 is equal to 1.116 x1. Remember, this is 0.01. The dot is somehow become insignificant. Let me put the dot, right? This here, right? There is the dot. Right. Then 0.116 x1 is equal to 0.01. So x1 is going to be 0.0862 meters. If you multiply by 1000, 86.2 mm. And using any of the equations one can estimate the value of thermal conductivity. For example, if you use equation A, m into x1 is equal to 0.236 and m is going to be 2.737, and for circular fins m is root of 4h by kd, and m square is going to be 4h by kd, and k is going to be 4h by m square d. And if you substitute for h, 25, m square 2.737 square, diameter 30 mm, 0.03, your k is going to be 444.77 watts per meter Kelvin. So this is a problem given in IS 2018. So these are some of the problems which are thought-provoking, and in these problems we have simply used the available equations. So based on this, one can have practice of some more problems, and one can have a confidence of doing any type of derivation or numericals. So with this, we will close the session today, and in the next session we'll try to have a look at unsteady heat conduction. So take care of yourself. Have a great time ahead.